appointment planning. And now we are talking about patient transportation this week and also next week. And the question is why it's important. And Sven's talk will also fit perfectly into this lecture content, because it's about how to bring the patient safe and secure to a particular ward or within a hospital. But the problem is it doesn't generate any kind of profit, okay? But on the other hand, it's extremely costly for the hospital. So we need patient transportation to ensure that on one hand patients receive timely and also appropriate care, obviously. That means it has to be safe and efficient, okay? And it sounds pretty simple because you provide patient from one location to another, from A to B, okay? But the question is how our techniques could be used for healthcare providers to optimize routes, schedules, but also resource allocation, okay? So that we can improve service efficiency and patient outcomes on one hand, and controlling costs on the other, okay? So it's an extremely expensive process in healthcare. And patient transportation can be, we have this following agenda. So first of all, we talk about definition and objectives, and then we start with optimization model, that is dial-right problem, a static one and a dynamic one, and then how to solve these NP-hard problems. We will finish then with a real-world case study at the end. Okay, so let's start maybe with a motivation, why it's so important to consider patient transportation. So here it's from 2010, so it's almost 40 years ago. A hospital in Saarland, Homburg, they complained that their patients have to wait much too long. Homburg, in former times, it belonged to Rhineland-Westphalia, and previously it was a psychiatric ward. And if Professor Nickel would stay here, he would make a lot of jokes about that. So I'm recorded, I cannot do that. But after that, you see this huge area with over 100 buildings, and patients have to be transported from one building to another. And this means we have a really challenging task, because we have this pavilion structure from the 19th century, over 100 buildings, and there's a road of 12 kilometers. Okay, so a huge distance that patients and transportation have to be carried out. And we have on average 450 patients per day. Okay, so it's pretty stressing on the street between these hospital wards. They had 37 paramedics to transport these patients, but on average patients had to wait 30 minutes for this transport, and in some cases they had to wait 1 hour, 2 hours, was not uncommon. And many patients complained that this is too long, because you have to imagine you don't feel well, you're sitting there in these kind of light coats, almost naked in some kind of corridor that is windy, and this is not really appropriate for a patient that doesn't feel well. And they already had hired more staff, paramedics, to improve that, but the problem is not only that staff is needed for carrying out transportation, but also to optimize the routes, okay? So we have to think about how that can be improved, all the processes, the routes, the schedules behind that. Okay, so this is basically the motivation, and here's a short joke. If you would like to cut the costs, you have to put as many patients in a vehicle as possible, and then if you waited for 2 hours, you should be happy, because then you can also leave first, okay? So this is a simple joke, how can we cut costs at the end. Okay, so there are different transportation models in hospitals. So we have, for instance, pickup and delivery services. These are processes that collect items from a specified location and deliver them to another specified location. So what could it be? Medical and nursing consumables, but also blood transportation. If you have the blood in a cooling room and then you need it for the surgery, that has to be transported. But also laboratory samples. If you have cancer and they take a sample of this, it has to be transported to a diagnostic ward where it is tested if it's a good one or bad one or whatever. And also, of course, repair devices have also to be transported. Then we have supply and disposal. These services involve the provision of goods and materials. This is the supply part, and then the removal and proper handling also of waste or unwanted items. This is the disposal. And these services are, of course, essential to ensure the smooth operation and maintenance of a clean and safe environment, especially in hospitals, obviously. But in hospital, laundry makes them up the largest part, which makes it a bit like a hotel, right? In some sense, at least. Okay. And then we have transportation services, in particular patient transportation, where we, it's very simple at the end of the day. We just have to transport a patient from A to B, okay? And then we have to differentiate, is it internal, so within the buildings, within the ward, or between the buildings at the same hospital campus, like we saw it in Hamburg, or is it external one, so like medical services, Sven will talk about that, to outsourced wards, or between also different hospital locations. So if we are not a specialized hospital, then we have to transfer the patient to a hospital that can treat them. Okay, and we will focus on the last part, the transportation service, and particularly the patient transportation. Okay. And you are in a university, so we need some kind of definition. So the first one is what is patient transport? This is simply on-time transportation of the right patient to the right functional department. This is basically the core definition of logistics, the right delivering the right product to the right customer at the right time. Here it's patient and wards, also by assigning requests to staff. So who has to handle that? Route planning, so the sequence of locations visited. First of all, the surgical ward, and then the diagnostic ward, and then the medical ward, and also the temporal determination of routes, which means we do a real schedule. So we know vehicle A will be at ward B at time 8 EM. Okay. It seems to be pretty simple, but we have, of course, many challenges that we have to face. Major hospitals, so especially in big cities, they have much more than 100 beds. In Hamburg, I think even more than 2,000. Even in Karlsruhe, we have more than 1,000 beds. And that means usually we have more than 200 patients each day. So we saw in Hamburg 450 even per day. And most transportation requests arise during peak times, especially in the morning after the medical around. So often in the morning when surgeries are planned, for instance, then doctors are going around and then suddenly they require new test results, a new CT scan because they say this is too old, we need a new one, blood samples, and so on and so on. And then in the case of 100 requests at the same time, of course, some patients have to wait. This is obvious, right? And this is why we have these peak times, especially in the morning. And then these often what happens in the hospitals, even nowadays, that they dispatch this manually based on, let's say, FIFO, first in, first out. So who's calling first will be picked up first, and every request is collected at the central dispatching center, so it's located also in the hospital. And yeah, we have this classical domino effect. So if a patient doesn't show up on time, then of course everything else will be delayed, okay, because they won't drive without this patient, okay, they will wait till the patient is there, and then they will leave. That means everyone else has to wait. Okay, but the good thing, or the question is now, we would like to improve the transportation of patients, but how to measure it? So at the end, we don't want to have gut feeling. We want to have quantitative measures to show, okay, if you do it like this, we can improve the what. And that's the question. Okay, what kind of criteria do we have to measure, to quantitatively measure performance? And we could measure total lateness. So of course, when the patient has to wait because the transportation is too late, it's inconvenient. Okay, the patient has some long waiting times. But on the other hand, we also have operating costs, because if the patient is not delivered to the right ward, also there, the MRI scans, the CT scanner devices and so on, they are empty, they are not used. So we have unutilization of devices. We have staff who are waiting for the patient and so on. So these are operating costs. Then total earliness, that means also being too early is also not good, because again we have operational costs, but this time on the fleet side, because now we have waiting or idle times of the transportation service. They are sitting around and are waiting till the patient can be delivered. Also what we can somehow measure quantitatively is the total driving time, which is the utilization level of vehicles and teams. So how long are they on the track? How long do they have to drive? And of course, here we have, if the longer the driving time, the more fuel we are using. This is also, should be balanced in some sense, especially for climate change and so on. And then on the other hand, we have total transport time for patients. And again, if the patient is picked up on time and then they start to drive with them 2 hours on the campus, then obviously this cannot be good for the patient. So again, we have this kind of dissatisfaction of patients. And then we can differentiate between what is actually user convenience or inconvenience. So what is, if we try to improve our transportation, is it from the patient perspective better, or do we want to improve that from the hospital perspective and try to improve the efficiency, the utilization of our devices, staff, and so on? So we have to differentiate that. And sometimes this could be conflicting and contradicting objectives, sometimes at least. Okay, when we look at these criteria measurements and we look at the user inconvenience, okay, then we know that waiting times, this is what can be measured, or also access ride time, if they are transported too long, in the vehicle, okay, they are spending a lot of time in the vehicle. Both can be measured in minutes. And on the other hand, we have efficiency. We can calculate and determine the transport cost, because fuel has to be paid, stuff has to be paid. Then we have travel times, and indirectly, again, fuel consumption, but also early pickup. Then it's too early, we have idle times for the transportation team, okay? So everything that you can see here could be used for penalties. You have a time window where it's absolutely fine that the patient is picked up and delivered. You have an earliest time, that's fine. It's latest time, it's also fine. But everything outside this particular time window has to be penalized. And you see that to be earlier has another shape than to be late. Okay, so we have an asymmetric penalty cost deviation and function, and that is always difficult to model. Okay, so imagine, okay, it's unrealistic, but imagine you are waiting for a bus and the bus is on time. Although I have to say the KIT bus to go to Campus North, I experienced they're really punctual. So the thing is, let's say you are waiting for that one and you are 30 minutes too early there, then it's inconvenient, right? You could do something better in this time. you have half an hour, you could do whatever, drink your coffee, read a book, whatever. So that's much too early. So it's inconvenient for you. If you are 5 minutes too early, it's okay. Okay, you can wait for 5 minutes. That's not an issue. But if you are 1 second too late and you couldn't get the bus anymore, then you have to wait for another hour. Okay, for this KIT shuttle. So that means your penalty cost or your cost for you, it's pretty high. Okay. That means you have a sharper increase here and here than in the case of need my laser pointer. So you have here a sharper increase, also here and here, than being too early. Okay, so you have this asymmetric penalty function, which, as I said, is difficult to model in an optimization formulation. Okay, and it's pretty similar for MRI scan. If you are too late, then another patient could use your time slot, and you have another half an hour, another 45 minutes. Okay, so being late could be a problem, a harder problem than being too early. And then that means we have some kind of conflicting objectives between efficiency, which is from the hospital point of view, and user convenience from a patient point of view. And before this patient transportation was, the hospital was aware of that, they focused only on one objective. For instance, minimizing the costs or minimizing the traveling time, something like this. And nowadays, they are starting to minimize multi-criteria with different weights. When they say, okay, my costs are more weighted than patient inconvenience, but still it's included in the objective function, and we can take account of these different objectives which could be conflicting. So overall, we try to get a better schedule, better transportation than only focusing on one objective. Okay. Processing of transportation requests. So we have basically, this is our planning situation. This is what we have. We have transport of patient on hospital campus, so between different hospital buildings. We have several hundreds patients services per day, so pretty much. And service requests are given to a central dispatching office. A central human is doing the transportation planning. This is based on manual handling, like FIFO, first in, first come, or first out. And manual pricing, so the transportation stuff is calling. Okay, here is schematically how it is used. We have the central office where the scheduling is planned, where the transportation is planned. Then the wards in the morning after the doctors went through all the patients and say, I need a blood sample, I need a MRI scan, and they're calling and asking, I need transportation for my patient A to ward B. And on the other hand, we have the transport staff. They are picking up the patient, delivering them to a particular ward, going back, and then they are calling the central office saying, okay, we are free now, we can take another patient, which is basically weird. Okay, so it shouldn't be like that. Actually, the central office should give them patients and should give them schedules, should give them the plan, and not waiting till they are calling, saying, okay, it's we are here, we can take some patients. Okay, so that should be the other way around. Okay, and also when we talk about them and asking them, are they punctual? So if they delivered a patient and coming back, are they on time then? And several years ago, they didn't know. Okay, so no one knew if they are punctual, if they are on time, if the patient was delivered on time or not. So the data wasn't collected. Okay, so often this information is not available, but it's necessary to also quantify and evaluate how good our transportation is. Okay, so really weird, but this is the planning situation. And this is an example, a schedule example from 2006, I think around 2006, when they did it manually. So you maybe see the cows already there. And the problems with manual handling is obviously that we could have late transport or low reliability, and no one knows exactly where's the transport, where's the patient, when is the transport where. So because of this manual handling, there's low reliability, okay, that the patient will be picked up on time. Of course, we have undesired waiting times and idle times. Patients have to wait on one hand, and the transportation team has also to wait, so there are some kind of idle times. And often what could be observed is that we have overworked employees and dispatcher, because often dispatcher, they prefer a particular staff members. They can communicate better, they're on time, they're reliable, whatever. So what they're doing is they ask always this particular staff members to carry out this transportation, okay? And what could happen, of course, that particularly these teams then are stressed, overworked, and also the dispatcher is under high pressure and time pressure, because requests are always coming in, then requests are cancelled, and so on and so on. So the dispatcher himself is under time pressure. And often, as before, we don't have enough data, we don't have enough information. So often, we had that before, patients are lost, okay? Because what could always happen is patients are waiting in the waiting room, then the transport is coming by and asking, we are free, do you have some patients for us? Yeah, the next one is coming in 10 minutes, but you can already take these patients. So they're taking the patients, the next vehicle arrives, and no one knows where are the patients, who took them, when are they at the ward, and so on. So this is very, very common situation to search for the patients. Could happen all the time. And then what was also observed is that sometimes they cancel appointment. So someone is calling and say, okay, I will cancel that, we don't need the transport anymore. And then a few minutes later they call and say, it's urgent, we need the transport right now. So what they are doing is across when they cancel the transport request and read if it's urgent. And then we asked the team, but from where do you know what came first? So if the cancellation was first or the urgency was come first, because the other way around is also possible. First of all, they're calling and saying, we have an urgent request, and then a few minutes later they're calling, they say, we don't need this request anymore. And the dispatcher said, no, I don't know, sometimes I don't really remember, and in the case, if I don't remember, then they send the transportation. So you can see manual handling has a lot of mistakes, errors involved that could be of course avoided if you have this in a digitalized way, okay? Because simply this dispatcher may not remember which came first, okay? So because sometimes the patient needs a surgery, urgent surgery, and then but for this they need some kind of sample, blood sample or whatever. They're calling saying we need an urgent diagnostic sample or whatever, and then the health status deteriorates so fast that they are calling say, okay, the surgery has to be carried out instantly. We cannot, we don't need a diagnostic result anymore. We will bring the patient instantly to the surgery ward. Okay, so this cancellation and urgency, they are pretty close to each other, and it could have significant consequences if the dispatcher mixes up. Okay, questions so far? Okay, then, no data, as I said before, okay, for quality and optimization. Okay, now if we would have a digitalized process, then we could also improve the transportation, the entire processes, and we could quantitatively measure the improvements, because we can now say by how much could delays be reduced, for instance. Okay, so we can decrease delays and waiting times for the patient, but also for the transportation team. Avoiding empty trips because and also cancellation of appointments. That doesn't mean we avoid the cancellation, but the problem is the lack of information. If they somewhat cancel the request, but the dispatcher didn't give it to their transportation team, they will still go to this ward to pick up the patient, but there's no patient to be picked up. Okay, so there some kind of cancellation of appointment that didn't reach the transportation team, and we have done empty trips. Then of course we could smoothen the workload, because we talked about peak times where we have a lot of requests at once, and with a optimized schedule and optimized transportation plan, we can also smoothen the workload for the transportation team and also for the patient, that they know instead of you will be picked up at 8 and then they will be picked up at 10. It's another issue if they say you will be picked up at 10 from the beginning on. Okay, so they know they don't have to wait for 2 hours. They can stay in their room. And also, of course, decreasing the costs. Okay. On the other hand, we have also qualitative improvement that cannot be measured that perfectly, but still, if we improve the process, we can see that patient satisfaction could be improved. We have more efficient staff planning so that they don't have too much idle times, too much stress at peak times, and so on. So also the staff satisfaction could be improved. And we have a databases for further optimization. Okay, so data collection is always a good, my former professor said, independently of where do you start to work, start collecting data from the beginning on. Yeah, because then you can evaluate the process, you can evaluate the improvements and so on. Okay, now we start with formalization, the optimization model, and with a dial right problem, DARP as an abbreviation. And this involves the planning and also the optimization of vehicle routing and also schedule. So which vehicle at which location at which time, okay? Where the customer, in our case the patient, specifies both the pickup but also the drop-off or the delivery location and also the times. And this is also important, not only the routes and the locations but also the times. And this services are pretty common in areas like hospitals, but also transport for people with disabilities or senior citizen transportation, but also other non-healthcare on-demand transit systems. Okay, this is pretty common one, and the idea is we have, we have vehicles, okay, we have a depot where they start and they have to finish their routes. Then we have nodes O, this is the original node where the patients have to be picked up, and then we have D nodes, the delivery points where the patients have to be dropped off, okay? And first of all, we have to take the decision which patients should be carried by which vehicle. Okay, so this vehicle is covering these nodes, this one is using that one, and this vehicle is covering these nodes, okay, on the campus where buildings are located far away from each other. So the first decision we have to make is the request clustering, okay, which vehicle to which patient. Okay, the second decision is in which sequence do we pick up the patient. Okay, so for instance, this vehicle is leaving its depot, picking up the patient at the medical ward, picking up the next patient, the second patient at oncological ward, and then delivering the patient to the first location and the blue patient to the blue location, and then on the way back to the depot, the vehicle is picking up the orange patient and bringing him to the orange destination ward. Okay, so from the surgical ward to the medical ward or something like this. Okay, so this is the second type of decision we have to make. And then the third one is to determine the real schedule. So often, schedule means simply the vehicle has to be at 7:55 at the blue location, at 8:10 at the green location, and then at 9 at the orange location. And what is often done is that the arrival times are always often fixed. So, for instance, the patient has surgery at 10 a.m. That means the patient has to be at the surgery ward at 10 a.m. and then you have to determine backwards when do we have to pick them up to be on time at the surgical ward. Okay, so the arrival times are the fixed ones, and pickup times, these are then the times we have to determine backwards. Okay, so often not the other way around. Okay, it's often that we know the destination times. Okay, so we have the clustering, we have the routes, we have the schedule. We know which patient at which time, at which node to pick up and to deliver. Okay, and now we have to put it in some kind of classification. So the overall umbrella term is the pickup and delivery problems with time windows. These are problems that involve optimization routes, but also schedules to ensure that customers, or in our case, patients, are picked up and dropped off within specific time frames. Okay, so it's like vehicle routing problems with the overall term that it's like the, let's say it's like the traveling salesman problem with different vehicles. Okay, and time windows. Okay, and time windows often refer to time intervals the transport arrives. This is often the case. However, we can also have time intervals when the product, the customer, the patient is picked up. Okay, so the DARP belongs to this overall, and if you are at a conference with vehicle routing researchers and routing or schedule researchers, in one room, they're always using this kind of abbreviations, and you cannot follow at all. So they love these kind of abbreviations, and you always have to know which letter stands for which kind of problem, because they are so detailed, with time, without time windows, or with coming back to the depot, with sub-routes, without, and so on. So there's a really vast variety of these kind of problems. And we have to differentiate these DARP problems in static and dynamic ones. Basically, so the static means the demand is known and is static. So we all know everything in advance. Okay, so someone has maybe an idea what a dynamic version of DARP could be? So if static means we know everything, the demand is known, so maybe on Monday doctors are calling and saying we need transport at 8 for 5 patients. So what could be the dynamic one? Static is static, everything is known. What could be the dynamic DARP problem? What could be changed there? Yeah, please. Okay, seasonal effects, interesting. So, but demand that is time dependent, right? Okay, what was your idea? Exactly. So we have to differentiate, and that was really good examples. We have to differentiate between uncertainty on one hand and time dependent on the other hand, because uncertainty doesn't necessarily means that it's the same as time dependent. Something could be time dependent, but still certain. So you could have requests on Monday saying we need 8 patients at 10 o'clock and we need 10 patients at 12 o'clock. This is dynamic still, because the demand changes over time, but we know that in advance. So this is still certain, okay? So, and uncertainty is something that we don't know, that could come in suddenly. We will come to this dynamic version in a moment, but let's start with the static formulation first, because our focus is on the transportation of people and minimizing the dissatisfaction on one hand, the cost on the other hand. This is the for the DARP, independently of static or dynamic one. Okay, so this is what I now present as a standard dial ride problem. This is not particularly valid for hospitals, but it can be used also in for this problem. So you have a set of transportation requests, and you have some kind of a map with a depot where you have origin nodes and destination nodes, so you know where to pick up someone and to deliver someone, products, customers, patients, whatever. And then you have a request I, so you have these origin nodes, you have the destination nodes, and you have the time windows for picking up, let's say the patients in our case, and the delivery time windows. This is the earliest possible time window you have to deliver the patient, and this is the last time you could deliver the patient. Everything outside is not acceptable. And then you have service time at pickup and also the delivery location, because sometimes you have a patient that requires more assistance because they cannot walk, for instance. They need a wheelchair, whatever. And then you have patients that simply can walk, sit in the vehicle without any kind of assistance. But you have to take this into account, that service time could be dependent on the patient and the health status of them. And also the maximum travel time. So again, the patient shouldn't be transported, for instance, for more than 1 hour. Okay, this is what we have to tell the model. Please pick up the patient on time, but don't travel with them over 2 hours or over the entire campus, okay, before reaching the destination node. Okay, and then we have fleet characteristics. So we know that our vehicles are restricted, so we don't have unlimited capacity available. We have maybe 3 seats or 2 wheelchair seats, stretcher or something like this, and they could be also located at different positions. Okay, that we have to take into account. Okay, and then the question is, find the route now with the minimum costs containing all the transportation requests. So what is necessary is that you pick up all the patients that have to be picked up. You have to deliver them on time, and the objective is to minimize the overall costs, for instance, for fuel or whatever. Okay. So our hospital under consideration, they have only few requests that are known in advance. We know that there could be some kind of unforeseen events, emergencies, or the treatment time was longer than expected. We have cancellation of appointments because the transport is not needed anymore. We don't know the travel times in advance, not the exact ones. Maybe you have to wait at the elevators. Okay, sorry. You will see later, because many hospitals complain that they have to wait a long time for in front of the elevator. But empirical data showed the opposite, because of course if we are staying in front of a closed door, subjectively you think you are waiting for ages, right? But objectively it's really minutes, even seconds, okay? But still the travel times might not be known. And then we have specific requirements of infectious patients in quarantine. And believe me, corona might be not the most infectious disease, okay? The most we are fearing. Okay, there are also other very, very cruel illnesses and infectious you don't want to deal with. And then sometimes you need some kind of presence of medical staff, additional nurse, whatever. You might need the medical equipment like wheelchairs and so on. And you have to take it into account that different vehicles could have different equipment, different space. This has to be also taken into account, and we are dispatching according to priority. If a patient is urgent, of course, we will handle them earlier than the others. And then these follow-up requests, this is also funny because every time when they are providing and transporting patients to an MRI scan, they are not planning the way back. So it's always a surprise that MRI scanner ward is calling and saying, okay, the patient's ready, you can take them with you back. And then they say, oh, okay, we have to plan that too, so we are coming in 1 hour or whatever. So these follow-up requests can also be planned in advance instead of ad hoc, which is often done in hospitals. Okay, and then this is a hard constraint. The entire demand, every patient has to be served, has to be transported. Okay, this has to be fulfilled by the optimization model. Then we have the other way around, where we talk about hospital specific. So we have heterogeneous fleet or transportation teams. Not only the vehicles are different, but also staff could be differently skilled. Could have different service or working hours. We could have part-time staff. We could have work breaks where the team has to have a breakfast or lunch break, whatever. Again, different equipment in the fleet. We could have multi-dimensional vehicles. We could either have 3 seats or 2 seats and a stretcher. We could also modify the vehicles, and of course the travel speed also depends on the vehicle. Okay, so now the model formulation for the static DARP problem. Okay, so now we have a static version. That means we know the transportation requests in advance, assuming that Monday evening we know all the requests for the Tuesday transportation. So we have static data, all the requests are known, the travel times are also known. So we are constructing the routes on Monday evening for the Tuesday. So we are doing that beforehand. And this is typically an NP-hard problem. These static DARP problems are generalization of these vehicle routing problems, the pickup and delivery, and also the vehicle routing with time windows. So if you hear that this is an NP-hard problem, what does it mean for you? I'm not talking about what is a mathematical definition, but if you hear a problem is NP-hard, what comes into your mind? Yeah. Exactly. Thanks. So it's believed at least to be unsolvable in polynomial time. This is a very simple definition of NP-hard problems. Okay, so therefore there are research proposed different types of solution algorithms, dynamic program, branch and cut, and heuristics, obviously, because the exact optimal solutions cannot be solved or cannot be provided in a reasonable time frame. Okay, so often heuristics are used. Okay, so here we have the model parameters. Okay, we have the node set of nodes, also consisting of the original one and the depot. So the depot, let's say, so you have a node. This is our depot, so starting point, and then you have some kind of demand nodes, pickup nodes, where you have to pick up the patient, and then this is basically up to n. You have n nodes where you pick up the patients, and then you have destination nodes 4, 5, 6, okay, where you have to deliver these patients, and this is simply n plus, okay, I. So these are the rest. And then you go back to the depot, which is then 6, that's 7. This is your final destination. Physically, it could be the same depot, okay? But for the optimization model, it's important that it is another node, Okay, so as I said, physically it's the same depot, could be the same, but mathematically is necessary to separate them so that you have a straight line between 0 and then going to the demand nodes, going to the delivery nodes, and then coming back empty to the depot. Okay, this is basically what is saying here, so that you have two copies of the depot, 0 and n, 2 times n plus 1. Okay, P, this is basically, so everything, this is P, so these are the pickup, and these are the delivery nodes you have. Can you read it? Okay. So, and then you have load associated to the vertex, which is basically your demand. So at each node, you have demand Q, that is the number of patients that you have to pick up. Then you have the service duration. So each ward, because I is the node, so let's say the patients in intensive care units, they might require more time loading them than some, for instance, oncology patients, because often they can walk by themselves. Just an example. So the service duration is depending on the ward and the demand node. They have to be picked up. And then the A is a set of arcs. So these are the basically the connections between the nodes. Okay. So I to J. K is the set of vehicles and routes, because we have to differentiate. Different vehicles could have different capacities. This is shown here. The capital Q is the capacity of vehicle Q at K. Then you have the maximal duration of route, because you cannot, you don't have enough fuel, for instance, so you have to finish after 3 kilometers or whatever, okay. Or 3 hours. Then you have the associated costs with traveling this particular arc from 2 to 3, some kind of fuel consumption. Then you have the time between 2 and 3, let's say half an hour you have to travel. And L is the maximal ride time, because we say the patient cannot stay in the vehicle for more than 1 hour, something like this. And then we have this time window where we have to pick up the patient or have to deliver the patient to the vertex I. Okay, so these are the parameters and the sets. So this is basically the input you have to give the optimization model. This is everything shown here is what you have to know. And the decision variables is the output of the model. So this is the result of the model. So what you are doing is you decide which arc you are using. So do you use from 2 to 3, or you don't? If yes, then X is Y is 1. If not, then X is 0 if you don't travel from 2 to 3. Then this is the time at which vehicle K starts serving vertex I. So the time when the vehicle is leaving node 2 at 8:15, for instance. Okay, this is U. W is the load, the number of patients you have in your vehicle, and R is the ride time of user I. So how long the patient is spending inside the vehicle. Okay, and our objective function is then minimize the total costs. Okay, then we have the constraints. So the first constraint is that each request has to be served by one vehicle. So overall K, we only have one vehicle covering this request. So we avoid that more than one vehicle is covering the same request. The second one is that we want to ensure that if a vehicle K serve a pickup vertex, so node 2 for instance, then it must also service the corresponding delivery vertex N plus I. So if the patient has to be delivered here, then this route has to be 1. Okay, this has to be the same. Okay, so that we have on the right hand side. So if you put that on the right-hand side. Okay, it should be the same. Okay, this is some kind of flow conservation. Sorry. Okay, so simply the meaning is that you cannot only perform pickup. You cannot only pick up the patient, but not delivering them. Okay, this is simply what ensures by 2. Then the third one, that you have to leave your depot and you have to finish your route in your depot. Okay, so independently of if you don't serve anything here, but still this has to be fulfilled. Okay, so you start at 0 and you finish in your depot. Okay, this has to be done because maybe you have more vehicles than a request, then an empty vehicle can also go from 0 to 7, but this has to be ensured that the route starts in the depot and ends in the depot. Okay, then the third one is simply, the third one. The fourth one is ensures simply that the number of times a vehicle enters a vertex I is equal to the number of times it leaves. So everything that leaves into that has to comes into the node, has to leave that again. Okay, it cannot simply disappear. Okay, this is also flow conservation. Okay, then we have the fifth constraint group. So this is to define the service time. So of course, U is the service time starting at node 2, at let's say at 8. Okay, so it starts at 8. Then in this surgical ward, they need 15 minutes to load the patient. So it's at 8, it is 8:15 plus the time they need to travel from 2 to 4, let's say half an hour. So that means the time at J, it's 8:45. Okay. If only under the condition that X is 1. Okay. Only if this arc is used. Okay. Then the 6 is define the vehicle loads. So this is the number of patients that were picked up at node 2, plus the patient that have to be picked up at Q, because what could happen is you go from this to this and then to the 4th node, so you have patients carried here and you pick up additional patients here, okay, and then you have so you have 2 here, patient 3 here, so overall you carry 5 patients to the 4th node. Okay, this is guaranteed by the 6th constraint group. The 7th one is to define user write times. So we are starting at U, and then of course when so if we are let's say if we are here at 10, then of course minus half an hour for minus. So if we are here at 10 and here we were at 9:30, okay, plus the duration, service duration, then you know how long the patient was inside the vehicle. Okay, so it's simply the arrival time at node 4 minus the starting time and the service duration. Okay. Okay, then 8 is the feasibility of routing time, so time for driving one route that cannot exceed, of course, our maximum duration time. So, okay, so on the right hand, you have this capital T. You cannot drive longer than allowed. Okay, and then the 9th, the feasibility of starting times. We talked about time windows, so the starting time in node 3 should be between 9:30 and 9:45, something like this. Okay, so it cannot be earlier and it cannot be later than this time window allows. The 10 is the feasibility of user write times. Again, here with the 7th, we determined the writing time for the patient, and here we say that the patient cannot be longer than the allowed time L in the vehicle, But of course, if the time between node 3 and node 4 takes half an hour, it cannot be less than that, okay? So we cannot jump, we cannot fly. It is at least the time for using and traveling from 3 to 4, okay, half an hour, whatever. And then the 11th one is simply that you cannot carry more patients than the vehicle capacity allows. If you have 3 seats and you have 5 patients, that cannot be. You can only carry 3 patients. Okay, questions so far? Okay, I realize that you don't talk to each other, and it's not healthy. And the problem is we are in a lecture where we talk about healthcare. This is why I would like to increase your health by forcing you to talk to each other and that you get to know each other. And therefore I would like to do some random group works. It's, don't be afraid, it's simply that you have to chat with each other, okay? After you're done your work, you can chat about your whatever, beer preference or something like this. So get to know each other. This is your main task. I would say randomly, the girls, you two, and you girls, you can do both one group, let's say of 2, maybe 3 people. Then maybe you guys in the back. So yeah, you both. Then you. We, okay, that's bad. Okay, you to the right, come here. And you are going to the group in the back. Yeah. So, yeah, you can come over and you go maybe. Okay. I turn off my So I hope it works again. So what you also realize that the objective function might not be the optimal one. It could be, it has some potential to be improved at least. Okay. This is why it's necessary to have also a dynamic version of the STARP problem. So first of all, the problem is that patient and vehicle-related events often force the change in the planned routes because, as some of you said, we have emergency, we have urgent requests that have to be also included in the plan. And we have patient-related events and fleet events. So patient-related events could be that we have the arrival of new transportation requests at short notice, no one knew beforehand. It could be that the data of requests changes and the dispatcher has no time to forward it to the transportation team, for instance, so they don't know what exactly happens right now. And of course, you could also have the cancellation of transportation requests. Some of you also said that. And on the other hand, we could also have vehicle-related events. So, of course, if you drive a long distance without brakes and without brakes, vehicles could break down, obviously. So we have to repair and maintain them, and also unplanned rest periods if the team itself doesn't feel well or needs a break or whatever. Okay, so this is what could be a problem, and therefore we need some kind of dynamic planning to also include new requests in existing tools. So we have a plan, but it could happen that we have to change it instantly to take care of an emergency and respond also to changes at short notice. Okay, and this is why we need a dynamic version of the RP. So the good thing about the dynamic version is that we lose a bit of NP hardness. I'm not sure if you are familiar with complexity theory, but when the input size grows, then the computation time shouldn't go exponentially, okay? So then the problem is considered to be efficiently solvable, okay? So if the computational time should grow at most polynomial and not exponentially, okay, with the input size. So for instance, a very classical example is the traveling salesman problem, where a salesman has to visit some cities to provide products and return them back to the depot, and they try to minimize the total travel distance or cost. So that if we would numerate and try to find the exact solution, then we have n to the power of 2 to the power of n possibilities, which means if he has to travel and visit 5 cities, then we have 120 possibilities. If we increase that to 7 cities, so 2 cities more, then we have, I think, 700 possibilities. From 5 cities to 6 is then 700 possibilities. You have to check which one is then the optimal. So you see that possibilities, the number of possibilities explodes exponentially and not polynomial. And this is why the dynamic version is a bit easier to handle, at least from the theoretical point of view. Because if we, for instance, plan for the next 15 minutes, 10 or 15 minutes, okay, then your input size is fixed, okay, so it cannot grow exponentially, okay, so because you have some kind of upper bound. So in the next 10, 15 minutes, nothing so special can happen. Not that many requests will happen. I mean, from the probability point of view, of course it could, but likely, it's not likely, okay. Therefore, you plan the current situation in some sense in a perfect way, okay, because you plan only for the next 10, 15 minutes. And this is why, in some way, you are losing some kind of NP hardness, okay. And what I would like to ask you now is just very briefly, 2 minutes till 10, how to change, or which parameters have to be changed in that static one to account for this dynamic nature. So if you go back to this one, so which parameters have to be changed, adjusted, for instance. Okay, just 2 minutes till 10 past. Okay, guys, some ideas. What has to be changed? Which parameters? Maybe which constraints? What has to be changed if I would like to have a dynamic version? Which parameter? If you don't have, if you have emergencies, for instance. Yep. Yeah, absolutely correct. So the first thing to be changed is, of course, queue. Exactly. So the load, so the requests of the patients, and it could be time dependent, right? It could be a function of you, for instance. Okay, so queue could be depending on you. If it's in a peak time, after the morning round is finished, then we have extremely high number of requests. So we have a high queue at this particular time in the morning, and then during lunch we have a very low number of requests. So queue is done depending not only on the ward, but also on the time. Okay, so time dependent. This is simply an example. Okay, so here what we know already that, of course, only few requests are known in advance. We need it before. We have unforeseen events that has to be put into the problem, which is so the dynamic version is simply an extension of the traditional DARP, and it also incorporates, and this is the main thing, is that incorporates real-time elements, okay, into the model. So as soon as new information arrives, the model will adjust and the decisions will be adjusted. So you have some kind of reschedule, re-optimization as soon as new information and new data is coming in. Okay. So of course you could also have this unknown transport duration because of waiting in front of the elevator. So what is needed is that we need a high flexibility. So we have a plan, a basic route, but that has to be re-optimized, rescheduled based on real-time data. Okay, so we need some kind of continuous re-optimization, okay, as soon as information is becomes available. Okay. And we also have to differentiate between the priorities. So is the patient an emergency, normal, low hazard, low priority? We have to, again, these time windows for pickup, but also for delivery. Then we have to take into account the mobility of patients. Could they walk, or do they need a wheelchair, stretcher, bed, whatever? Do they need, for instance, particular equipment, incubator, oxygen mask, and so on, depending on the status? And then we have this chain of requests. So, for instance, when a ward is calling and asking, can you pick up my patient? Indirectly, the transport and this dispatcher should know what is needed for this particular patient. So it could be that the surgical ward is calling and saying, we need a transport for 10 a.m. They know, the dispatcher should know that for this particular transport, they need some kind of physician or a nurse, additional nurse. And this nurse has to be picked up before we pick up the patient. And this is this chain of requests. And of course, at the end, this nurse has to be brought back. Okay, and this is a chain of requests that cannot be disrupted. Okay, we cannot pick up the nurse, going to another patient to 1 and then to 3, and then later going to the delivery point. This is not possible. Okay, so we are picking up the nurse, going instantly to the patient who is needing the nurse, and then after the delivery is done, then the nurse should be provided back. Same, this is again a chain of requests, transportation of infectious person, because the patient is delivered, but then the entire vehicle should be cleaned, and we have idle time, and this takes for 1 hour. This has to be taken into account, because we know after the infectious patient was transported, we need 1 hour to clean the vehicle. So this vehicle is not cannot be used then in the next upcoming hour. Okay, this is blocked, and this is what the static version, for instance, didn't account for. But this is this chain of requests that cannot be interrupted. Okay, and then so critical location. So critical location simply if we promise that the patient will be at 10 at particular ward, then of course we can. This is a critical location. That means at 9:30 they have to be picked up at the home. So we cannot. This is also the critical location, and this is what we have to we cannot violate that. Okay, so this is a critical location, the pickup and also the delivery location. And then we have particular time windows where we have to pick up and to deliver the patient. And the problem is that this critical location is always the first stop, obviously, because otherwise we would violate the time window we promised to pick them up. And then for this, we have some kind of penalty cost from deviations from this time window. We could have not critical patients, bless you. We could have non-critical patients, but that there are no penalty involved if they are picked up lately. Okay, that's fine. Okay, and then I would skip that. I think this is, maybe we can talk about that next time. I think it's time. Thank you for your attention and that you were willing to talk to each other. Next time, another group meeting. Yeah, thank you. See you next week. Bye.